one interesting thing to keep in mind as a structural engineer is that we just talked about trusses, right? And so we know that trusses transfer forces primarily through axial behavior, right? Those truss members are either in tension or compression. You don't really consider shear or moment when we're designing truss members. Sometimes we may have some shear and moment in the top and bottom chord members, but usually that is very minimal compared to the magnitude of the axial forces that they carry. And this is similar to the behavior of braced frames. So if you have a large-scale braced frame structure, such as the John Hancock Center in Michigan, then you can look at that, and the nice thing about this building is that its structural system is exposed, so it's integrated with the architecture, with the aesthetics, and you can look at that and you can see the actual truss configuration of those braced frames. So something to keep in mind when you see those types of systems. That also means, of course, then those diagonal members are transferring lateral forces through axial behavior. All right, so today's focus is going to be on cables and arches. We're also going to spend some time talking about general assumptions for elastic structures and basic reaction calculations, things like that. So there are the skeleton notes associated with this lecture, which we will dive into. I just have a few introductory slides that mainly focus on cable and arch classifications. So we'll start with that. Don't forget, homework 3 is due next Monday. Any questions on that so far? Yes.
So for my answer to the first question, I got downward force for the roller joint,
Okay.
which like theoretically shouldn't happen with a roller joint, but is that just assuming that there's no, is that like?
So, no, it's not necessarily incorrect. So remember that a roller, we idealize like this, but unless you're told otherwise, you should assume that it can provide a reaction in the vertical upward or downward direction, right? So remember back in the first couple lectures when we looked at actual connections and supports, how we had roller joints a lot of times, in steel members, right? They might look something like this, where you have long slotted holes with bolts, right? The bolts would be something like that, but those long slotted holes allow for some horizontal movement, but this would definitely be able to produce a downward reaction, right? So yeah, so that's not necessarily incorrect, yeah. It's always a good idea to also intuitively, right, look at it based on what the loads applied are and think to yourself, does it make sense that this reaction is downward? So yeah, so I encourage you to do that, yeah. Good question. Any others? Okay, good deal. So the assigned reading for today's lecture is section 510, and also the handout that's contained within your skeleton notes. So for some reason, your textbook, it's great, I really like it, but for some reason, the authors chose to not talk about cables at all, which really surprises me. So that's why there's a handout included in your skeleton notes that covers cables. And it's a short reading, all right? But that one also covers arches as well. And then section 510 will essentially cover the rest of the stuff that we're talking about in this lecture. And I think arches as well. All right, so, and interestingly, the handout that's in your skeleton notes is from the textbook, an older textbook that your textbook was sort of developed based on. So I really find it interesting that they chose to omit the section on cables. It's not even, doesn't even have to be that long, but anyway. There could be a whole textbook on cables. Like, it's a really complicated, they can be really complicated, the analysis. We're gonna keep it simple in this class. So Essentially, right, just some basic cable characteristics, right? Cable segments, we consider two force members, right? The cable itself is a two force member. As we talked about before, right, those two force members are axial tension only in the case of cables and ties. It can't support compression or transfer compression. We assume that they are pin supported at wherever they're supported, right, at the ends. And the thing that we have to do in order to be able to analyze cable forces, we have to assume the displaced shape of the cable under the loads that are given. So this is different from our other structures, right? The reason for this is because the cables are flexible with regard to other directions, right, or other forces. The tension is maintained, but the geometry of the cable, as you'll see, will be proportional to the forces that are applied. And this is technically a second order analysis. We can make some simplifications to certain types of cable configurations, and that's what we're going to do in this class. But if you have, for example, catenary action or a different type of cable load support attachment, which we'll look at in a moment, then it becomes a pretty complicated analysis. So the note down here says, technically, right, cables can support vertical or transverse loads. So the applied load doesn't necessarily have to be a vertical or in the direction of gravity, but if it is just a vertical load, then that simplifies a lot of our analysis and we can make certain assumptions. So we'll see that as we go through this. All right, so there are two different categories of cables. One is what you see on the left, which is the pin type connection, or you can think of it as the ski lift type connection. This is where the load grabs onto the cable and moves with the cable if the cable moves, right? And in the case of a ski lift, of course, the cable is moving, but that's not all necessarily the case like traffic lights, right? Then the other type is the pulley type, where the load kind of sits on top of the cable. The cable itself doesn't move, but the load moves along the cable length, right? Now, these two different categories require different analysis approaches. Basically, right, the pin type or ski lift type is what we're going to be dealing with in this class. That one breaks the cable into individual segments. The tensions will change from segment to segment, right, across a load. But it's a more easy analysis. And the pulley type is a little bit different. It's one cable segment, really. The tension doesn't change between, right, between the two ends. So it's the same magnitude tension from the entire length of the cable. But it's a much more complicated analysis. So we're not going to do that in this class. And then you can have uniform loads that you need to consider on certain cables, right, such as a suspension bridge that supports the deck and that effectively acts as a uniform load on that cable. So this would be a parabolic deflected shape that we would assume, and you can calculate. We could actually do that in this class, but we're not going to. But that's not too difficult. You're just using the geometry of a parabola. Catenary action is a little bit more complex. This would be an example if, for example, if you had just a cable that has self-weight as its uniform load, where the self-weight is significant enough to generate that catenary shape. Now, in theory, right, if you take a cable, analyze it with point loads, flip it upside down, all right, then you would have the geometry of an arch that would theoretically be in pure compression. Since a cable cannot take compression, it's only tension. If you flip it upside down and then flip the loads as well, that would theoretically give you, again, an arch that is in pure compression. So that is the approach that drove the design of this structure. Does anybody know what this is? It's the Sagrada Familia. It's in Spain, and they started construction back in, I don't remember the exact year, but the 1800s, right? So it's been under construction for a long time. It's still under construction today. I think they were trying to, they thought they would finish it by 2021 or something, but COVID delayed a bunch of things, and so it's still under construction, but this was designed by Gaudi, and his whole idea was to create these tall arches that are effectively upside down cables. So it's pretty interesting, right? Interesting case study. All right, so now moving on to arches. Of course, arches, their primary internal behavior is axial compression. 3 different types of arches or categories, if you will. You've got a thrust arch, which has fixed or pinned supports. All right, this is indeterminate. A tied arch is an arch that's simply supported at the 2 ends, and there's a horizontal tie between those 2 endpoints. That's the tie behavior is essentially going to prevent those ends from pushing out, right? So a lot of times, so the picture that you see is an example of a tied arch, that's a 3-hinged arch. But a tied arch, right, a lot of times the tie doubles as the bridge deck. So, it's provides multiple functions there. And a 3-hinged arch is one that has pin supports and then an internal hinge at the top. Technically, this is also a type of thrust arch. So in this class, we're just going to be dealing with 3-hinged arches in our analysis. Here are a few examples of each of those types of arches, right? So the St. Louis arch there, that's a very large thrust arch. The supports are fixed at the base there. The thrust arch, a pinned example of a thrust arch is shown in the upper right. Does anyone recognize that bridge? Yeah, it's the bridge that's by the Hoover Dam. So you can't tell from the picture, but the supports at either end are pinned. And then below you have an example of a tied arch that's simply supported. So the bridge deck here acts as the tie. All right, so now a brief introduction to structural reactions. Some basic assumptions that we make. First, we assume elastic behavior, right, in this class. That leads us to a next assumption that deflections are very, very small, all right? So in that line of thinking, any structure other than a cable would undergo deflections when exposed to structural loads, but we assume that those deflections are so small that they won't impact the geometry significantly enough to change our analysis, right? With a cable, that's different. We can't assume that the vertical deflections are small, for example. We have to assume a geometry under a given set of loads. But with cables, as you'll see when we get into it, we do assume that the axial deformations are small for given segments, right? So we assume that the cable segments do not change length. But again, we can't ignore the vertical deflections on a cable. And then if we have elastic behavior, we can apply the principle of superposition, which means that we can take individual loads, analyze them separately, right? Get individual sets of results for those loads, and then add the results together to get the effect of all the loads happening at the same time, all right? So we'll look at that. And here's a few examples of, right, beams deflecting, right? The concrete beam that you see is being tested, and you can see the cracks that have occurred. Those are flexural cracks. So you've got the tension at the bottom, right? And that's where the cracks will start, and then they'll propagate towards the top where you have compression. So this beam could potentially still be elastic. If you remove that load, it may return to its original position. I don't really know exactly. It depends on whether the steel has yielded inside, but it doesn't appear externally to have any definite signs of permanent failure or permanent yield. This, however, is very obviously no longer elastic, all right? So this has been pushed to failure. It has broken in a way that the deflected shape is two straight lines, right? You don't see a curve. So if the deflected shape is all straight line segments, that's an indication that you either have an unstable structure to begin with, or your structure has failed and now it's unstable, right? All right, so quick demonstration of the principle of superposition, right? It's what I explained earlier. If you have two different sets of loads shown on the right side, you can find the reactions separately and then add them together to represent the effect of all of those loads occurring at the same time. We can apply this to internal forces, deflections, stresses and strains, and so on. So there's an example in the skeleton notes that we will take a look at as well. So here you have 3 loads on this simply supported beam. And on the left side of the page, you can see the reactions calculated for each of those loads separately and then summed together to determine, the reactions for all loads acting at the same time. On the right side, you have the deflection at the center, the mid-span, right? So the center point along the length of the beam, that's the lowercase delta c that you can see there, noted for each individual load case and then summed to get the total deflection for all loads combined. The deflections are often tabulated in appendices of textbooks. So in your textbook, this is in Appendix D. There's also, so here's an example. I don't think this is the same table that's in your book, but this is the table that you would see when you take the FE exam in the FE handbook that you can get from NCEAS. So this is one page, right? There's another whole page and then a third page with just one entry on it that you'll see in that handbook. But basically what you do is you go to the table and you find the scenario that matches the load that you're evaluating, right? So for the point load, you would pick this one because that point load was located about a third of the way from one support. Or actually, I think it was, or a quarter of the way, I don't remember. But anyway, so you would pick the point load that is not at midspan, right? Because the point load wasn't at midspan. And then over here, you have the deflection equation, right? So you just plug in values for x, which represents the location where you want to calculate the deflection. Since we're looking for the center deflection, you would plug in x equals L over 2 to get the deflection at the center. And then B would be 120 inches to represent the distance from the end of the beam, right? And I've got a note there that this is the reverse scenario from the example. So let's see, right. So you just have to think about right, where your point load is with regard to the supports for that. And then, so the reverse, I meant to comment on that. So the reverse scenario means, all right, in this table, this is saying that this equation applies when x is between 0 and a. All right, so we have that. And then b would be the distance from that right end. All right, so 120 inches is the 10 feet, all right? Even though we have the point load closer to the left end, we just have to kind of flip it in our heads, right? And then for the moment, all right, same thing. You find the beam that fits and the load scenario that fits what you're looking at. Use the equation. Here it's pretty straightforward. You can just plug in x equals L over 2. Because it's a simply supported beam, it doesn't really matter which side the moment is applied since it's at the support. And then the last one, all right, this is actually not specific enough to get the right answer for our example. That's an indicator that when you take the FE exam, you shouldn't have something as complicated as that example. The difference is in the example, the uniform load isn't over half of the beam, right? The uniform load is only over a third of the beam length. So it's not quite going to get us the correct answer. You could use this to get a conservative estimate, right? This equation, and plug in x equals L over 2 to get the center deflection. But you would need a more specific entry that is usually not found in most books or tables anymore. I found this one in an old copy. But here you can see this is a variable distance from the support instead of a specific halfway point, right? So just to give you an idea of how to use those tables, and then a little plug here. I know most of you probably aren't thinking much about the FE exam yet, but you can go ahead and create an account with NCEAS and access the handbook, right, the digital copy of the handbook that you will be using when you take that exam, right? It's a reference book with a bunch of equations. It's pretty long, but it's a good idea to just get familiar with it, and the sooner the better. So I encourage you to check that out. All right. Any questions before we jump into skeleton notes here? All right. Good deal. So a lot of this stuff I already covered in the handout, but I'll just touch on it and make a few notes with you here. So of course, our basic assumptions are for an elastic analysis. All right. So all of these only apply if the behavior is elastic. And then again, the principle of superposition, right? We can calculate any of these structural responses that way. So quick note on these responses. So reactions and internal forces, these types of responses are completely independent of the material and the cross-sectional geometry, right? So E and I do not factor into internal forces or reactions. So you don't need to know that information to get that info. Stresses, strains, and deflections, on the other hand, are tied to material properties, all right? And stresses and deflections specifically are also tied to the cross-sectional geometry, right? All right, so here's that example that we just looked at. Again, Appendix D in your text. for those tables, okay? And I'll just note on here, delta C represents the deflection at midspan. You folks writing? All right, so now we'll start thinking about what a difference it makes if we have a continuous beam, all right, versus a beam of multiple single spans. So first we'll consider the simple span configuration, all right, and then we'll apply it to a bridge that's 250 feet long with 3 different spans. And remember the definition of a span, it's the distance between supports, essentially, right? So, and usually it's the horizontal distance between supports when we're thinking about members that span horizontally. So here, right, of course, you have the moment diagram for a beam with uniform load. I encourage you all to commit this formula to memory, right? That the maximum moment is WL squared over 8, and that maximum moment will occur at midspan when you have a simply supported beam with a uniform load. You can also remember that the reactions will be equal in magnitude, being WL over 2, since it's symmetrically loaded and symmetrically supported. All right, so now that we've established that, let's look at this situation where we have a 250-foot bridge that's broken up into 3 different spans. So if we have just simple spans, all right, then the deflected shape of this beam would be something like this. All right, just the simply supported beam deflection. Your moment diagram, right, would look something like this. I'm going to note where the supports are. All right, where the maximum moment in the 50-foot spans would be 940 kip feet. I'll add the units on the axis there. And then the maximum moment in the 150-foot span would be 8,440. All right, so obviously not drawn to scale. Now, the benefit of this configuration is that it's determinate, right? It's easy to analyze. All we have to do to get those maximum moments is use this formula. But let's look at what happens if we make it a continuous beam, all right? So now it's indeterminate. It's more complicated to analyze. The deflected shape, right? So we're just going to do an intuitive assessment here first. The deflected shape would look something like this. All right, so we would have some negative bending over the internal supports there. And the moment diagram would look something like this. All right, so again, I'll note the maximum values and in kip feet. So we would have some negative moments over the supports, and those values would end up being negative 4,770. And the maximum positive moment would be 3,670. All right, so if we compare the maximum moment in the first case to the maximum moment in the second case, this one is a much smaller moment, right, in magnitude. The sign, right, doesn't really matter as far as how large you need to make your section, right, because what we need is the magnitude of that moment. Remember, the sign just has to do with the direction of the bending and which side will be in tension versus compression at that specific location. So since we have a much smaller magnitude in this scenario, that means that we can use a smaller section and it's a more efficient design, right? So even though it's a little bit more of a complicated analysis, like I didn't get these numbers by plugging in an easy formula, right? This would be done using maybe a finite element software program or some other advanced approach to calculating moments. All right, questions? Okay. So one of the reasons that I went through that example, right, to demonstrate that beams often benefit from becoming indeterminate, right, as far as efficiency goes. That's not the case for arches. So we're going to look at a three-hinged arch, which is a determinate structure. But as you'll read in the book and the handout here, there's really no benefit to making this arch indeterminate as far as the size of the arch goes, right? It's not going to become more efficient structurally. So some major features about the three-hinged arch are summarized here. Of course, I mentioned them earlier, but you've got hinges or pins at the ends, right? So pin supports. And then a hinge at the top. So I'm going to change this because center point isn't really generic enough. Sometimes it is the center point, but really this should say top. All right. So to analyze this, I'm going to first label the points of interest. So we have A, we'll call the hinge B, and then the right support C. We've got our reactions, AY and AX, CY and CX. All right, and initially I'm just assuming everything in the positive direction, but intuitively, right, you can deduce that your CX will actually be in that direction to hold that arch in place, right? Because the arch wants to move out like that, so the reaction forces have to oppose that. So if you want to intuitively, right, just flip this around to start with, go for it. All right, so we'll start with the entire structure. And we're not going to be able to solve for anything directly yet because we have too many unknowns on the entire structure. But we're just going to set up the equations because we'll use them eventually. All right, so if we sum forces in X, we have AX plus CX equals 0. Summing forces in Y, we have AX, or AY, right? AY plus CY minus the sum of the applied loads, which is 50 kips, is equal to 0. And then summing moments, all right? We want to be strategic here. At this point, it doesn't really matter which support you pick. I'm going to pick the left side. So I'm going to sum moments about A. So that will give us an equation in terms of Cx and Cy, right? So we would get 75 Cy minus 20 Cx is equal to 2250. So I'm going to call that equation 1. All right, so we're going to use that when we break the structure apart at the hinge, which is going to be the next step. So remember, the benefit of having an internal hinge in your analysis is that you can break the structure there and you know for a fact that the internal moment at that location is equal to 0, right? So that eliminates a standard unknown for us, and we can use that to our advantage. All right, so we're going to break the structure at the hinge, and then we have a choice. We can use either side as our free body diagram, but which side should we choose for our solution based on what we've already done? We want the right side, right? Because if we isolate the right side, then we have the same two unknowns on our free body diagram, and that's what we want to use since we already have an equation in terms of Cy and Cx. So now I'll note equilibrium of the right side. And I'm just going to sketch a quick free body diagram. So we have Cy, Cx, and then we have a 20 kip load here and a 15 kip load at the hinge. We also expose the internal horizontal and vertical forces at the hinge. And the distances that we have are 15 feet on either side of the 20 kip load. All right. So what's our strategy? What equilibrium equation should we use here?
Some moments at B.
Exactly, yeah. If we sum moments at B, then we get immediately another equation in terms of Cx and Cy. So that equation will be 15 minus 1.5 Cy is equal to Cx. All right, so now from those two equations, we can solve for Cy and Cx. So Cy would be 24.3 kips upward, and Cx would be negative 21.5 kips. Negative sign just means we assumed the wrong direction, right? So correct that in our final answer. And then going back to the entire structure. All right, from summing forces in X and Y, we would get AY is 25.7 kips and AX is 21.5 kips to the right. So pretty straightforward solution. You just have to, remember to break it apart at the hinge, and then you're going to have two equations and two unknowns. Questions? Okay. Oh, Lorraine. All right, so here's the handout. read the section on cables, right? So now we'll introduce cables a bit, and we probably won't get through the whole example today, but that's okay. We can finish that up on Friday. So, of course, cables are two-force tension members. The assumptions we make include that the cable segments carry no moment, shear, or compression. We also assume that they cannot stretch, all right? So that's what I was talking about earlier. We assume that the axial deflections are negligible. And we assume that the self-weight is negligible. And for cables that carry, heavy vertical loads, that's generally an appropriate assumption because the self-weight is very negligible or very small compared to the forces that the cable supports. Again, if you just have a cable that is only supporting its self-weight, then you have that catenary behavior to think about. All right, so when cables have concentrated vertical loads, the deflected shape of the cable is assumed to be straight line between loads. So at any point along the length of the cable, sum of moments has to be equal to 0, right? So that's one of the just static equilibrium equations. It's true for all structures, all stable structures. So if the sag is known at one point along the length of the cable, then we can solve for the reactions and the sag at any other point. And then with that information, you can calculate the cable tensions in all of the segments. And so that leads me to the next point. At any point, the resultant cable tension is the square root of the horizontal component squared plus the vertical component squared. All right, so this is where you can really see that the internal forces, those cable tensions, are proportional to the geometry of the cable, right? Because when we assume straight line segments between applied loads and supports, what we have are triangular, right, pieces, right? You've got the length of the cable and the vertical and horizontal components of that length. That triangle of the geometry is proportional to the tension in the cable. So you have the horizontal component and the vertical component and the cable tension. So if only vertical loads are applied. All right, there's still going to be a horizontal component in the cable tensions, of course, but that horizontal component will be the same in every cable tension, or in every cable segment, right? Say it is constant across all segments. All right, so down at the bottom of the page, you have a fairly condensed little example there, but it is complete with finding the reactions, cable tensions, as well as the unknown vertical distances, right, that are initially unknown. So you start off with 4 unknowns externally, right, 4 reactions that are not known, but you know that vertical distance at point C. So with that information, right, you can break the cable at that location and start solving for the forces. All right, questions? Okay, we'll do the example next time. Since there are a few moments left, I'm going to show you, I have a thing on trusses to show you. So I'll switch gears for a moment. All right, so here, this is a photo I took of a truss in a local establishment. I don't know if anybody, I wouldn't expect anybody to recognize it and know what establishment it is. It was a cafe. And here, right, you can see this is a roof truss, or it's supporting the roof. You've got top and bottom chords are steel I-beams, and then the web members consist of, the vertical ones are these wood posts, and the diagonals are ties, right? So those ties would be tension only. So you can just kind of gauge by looking at the configuration and understanding how the load is coming in, right? So it would be a gravity load on the top chord. You can intuitively or just qualitatively assess how those forces are going to flow through the truss, right? What is the load path of the truss? And another thing I want to point out too, right? If you look at the top chord, what's something that's different from what we assume in truss analysis? How are the loads applied?
They're not the joints.
Right, exactly. It's essentially a continuous load application, right? But we assume that the loads are only applied at joints in our analysis. So this is where it gets into, all right, so technically we have a distributed load on top of that, on that top chord, right? But still for our analysis, it's acceptable to use the idea of tributary width to distribute those distributed loads or to condense those loads to point loads acting at the joints for analysis. So here, right, I show what we would have. We'd have those point loads acting at the joints. The top chord would be in tension, bottom chord in compression. Right, those diagonals would be in tension, and the vertical web members would be in compression. So I think it's, a pretty cool exercise. Next time you're out and about, you see some exposed trusses, take a look at them and see if you can assess, how those members are transferring forces through the truss. Questions? Yeah?
Why do you think the tides are all in one direction? They don't put the tide in the other direction to?
Oh, okay. Yeah, great question. So they don't expect these ties to ever be in compression, so that indicates that they don't expect the load to ever reverse, right? So it's just always going to be a gravity load. They probably don't anticipate many other load cases. So that's probably the reason. Because otherwise they would need to have something to be able to resist a load reversal there. And sometimes we have to consider load reversals, like in the event of seismic activity. But with regard to vertical loads, it can happen. So they may have done that analysis and determined that the load reversal would not be significant enough to counteract the effect of that gravity load from the weight of the roof. Or maybe this truss is not necessary for the lateral force resisting system, right? It's just part of the vertical load. So, yeah. Questions? All right. Well, thank you all for your attention, and I'll see you Friday.